Okay, so we have been talking about photolithography. The first step in photolithography is to create the mask, and the mask design would depend on the design of the structure that we want to fabricate. Okay, and the first step in the fabrication is to clean the wafers. So we talked about RCA1 and RCA2 cleaning procedure, and after cleaning the wafer, the procedure would be to grow an oxide layer. Oxide layer will be important in situations where we want to passivate electrical connection between different parts of an electrode or between electrodes, and it will be also required to enhance the bonding between the photoresist and the silicon wafer. Okay, so let us look at what oxidation process is. So silicon dioxide, if you look at the atomic structure, it has 4 oxygen atoms surrounding the silicon atom, as you can see here, and the silicon dioxide has 2 different types of forms. One is a crystalline form in the form of quartz, and the other is amorphous, which is the form that we get if we grow oxide using thermal deposition. So thermal oxidation is more commonly used in thermal ovens, so oxidation furnaces. For growing oxidation below 1 micron, we use dry oxidation, wet oxidation, or pyrogenic oxidation. So if you look at the chemical reaction, what happens in a dry reaction is silicon reacts with oxygen at a relatively high temperature, which is about 900 to 1200 degrees centigrade, to give silicon dioxide solid. Okay. Now in steam oxidation or wet oxidation, silicon reacts with steam at high temperature to give silicon dioxide and hydrogen. Okay. So the difference between wet and dry oxidation is that the wet oxidation is much faster, but there is difficulty that the quality of the oxide that we produce is poor. Okay. In oxidation, in dry oxidation, although it requires it takes more time to grow the oxide layer, the quality of the oxide layer is very good with much higher density as compared to the wet oxidation or steam oxidation. Okay. So the thermal oxidation is done in a oxidation furnace similar to the one that is shown here. So what we see here is the high temperature that is maintained inside the oxidation furnace. So typically there will be a board where we can stack multiple wafers, okay, and using a glass stick we can place the board inside the furnace. So it moves very slowly with time. So we know how much time the board needs to stay inside the oxidation furnace. So accordingly it moves from at one end and it can come out at the other end. Okay. So this is a typical oxidation furnace that is used to grow oxide layer. So here on the right you see different oxidation processes. One is the dry oxidation, which uses oxygen and nitrogen in the furnace. In wet oxidation we use in addition to oxygen and nitrogen we also use steam. Okay. And in pyrogenic oxidation, in addition to oxygen and nitrogen we also use hydrogen. Okay. So hydrogen can burn itself, which that is the reason why it is called as pyrogenic oxidation. Now if we have silicon dioxide layer which is thicker than 1 micron, there may be issues with delamination, because the larger the thickness, the difference between the thermal expansion coefficient of silicon dioxide and the silicon, there may be tendency of that layer to come out from the surface of the silicon if the thickness is higher. Okay. So once we oxidize the wafer, the next step is to spin coat our photoresist, which is a photosensitive material, onto the surface of the substrate. And the way we do it is by using a spin coater. Okay. So if you look at here, so typical spin coater is shown here, and a spin coater will have a vacuum choke which is connected to a vacuum pump. Okay. So to create negative pressure, so that it can hold the substrate onto the choke very tightly, because we are going to spin the substrate, and then we dispense the photoresist onto the surface, and there is a motor which would drive rotate the substrate or the chuck holding the substrate at the required RPM. Okay. So this is what you see here. This is a typical spin coater, and here this is the vacuum chuck, and we are placing the wafer on top of this and dispense photoresist, and this is the lid which is closed for safety, and then this motor underneath here will rotate the chuck at the required RPM. Okay. And there may be different recipes that you can build in onto spin coater, such as the acceleration time, from 0 speed to a fixed speed, what is the time that it can take to reach that peak speed, and at that peak speed, peak RPM, how much time it needs to rotate. Okay. So all those things can be programmed onto this spin coater. Okay. So this is the procedure. You place the wafer on the vacuum chuck and dispense the photoresist, and then we spin the wafer or the chuck at high RPM, typically 500 to 3000 RPM is used in spin coaters, and depending on the viscosity and the required film thickness, we can adjust the speed. So this is the thickness of the photoresist, which is dependent on the concentration of the polymer, okay, the photoresist, and the viscosity, and it is inversely proportional to the rotational speed. So higher the speed, we end up getting lower thickness, higher the concentration of the photoresist, we end up getting higher thickness, and higher the viscosity, we get higher thickness, and K is a calibration constant which can be determined from experiments. Okay. And alpha, beta, gamma are also the exponents of concentration, speed, concentration, and viscosity, which can be determined from experiments. Now when we spin, we dispense photoresist, and when we spin the wafer, the photoresist would due to centrifugal force, it will go towards the edge. Okay. But there would be always an edge effect where more of the photoresist will be around the edge of the wafer. So this is what you initially observe, but then as the speed increases, typically in a spinning process it may be 2-step process, or sometimes maybe as high as 5 different steps you can have. So as the speed increases, this photoresist which is around the edge of the wafer, it gets displaced. Okay. So at low speed, the thicker SU 8 around the edges form what is called the build up edge. Okay. And this is because of the surface tension, high surface tension of the photoresist, and it is very important to maintain a good quality coating on the substrate, because a good quality coating would lead to a good quality surface on a substrate and the further processing of the wafer. Okay. Now if you have too much resist that we dispense on to the substrate, if the quantity is more than what we require, then you would have the edges of the wafer will be covered with SU 8. Okay, so you will have a thicker, more material around the edges of the wafer, and in some cases you would also form ridges in the photoresist surface. On the other hand, if you have too little than what you require, then some of the areas of the photoresist of the wafer will not be covered by the photoresist. And while you are spinning the photoresist onto a wafer, there are techniques like reflection spectroscopy, which can be used for monitoring the thickness of the photoresist while you are spinning it. So this is what you can see here. This is the reflection spectroscopy technique, which can be used for online monitoring while you are spinning the photoresist. So you have an illuminator, light which comes through a filter and lens probe, and it hits the wafer, and the reflection light comes in, and using a photodiode spectrometer we measure the intensity of the light. So depending, by comparing the incident intensity of the incident light and the reflected light, we can calibrate the thickness of the photoresist. So with suitable correlations, the difference between the incident and reflection intensity of the light, we can predict how the thickness of the photoresist layer is. So typically in the resist, in order for the photoresist to spin, we use solvent. Typically 15% solvent is used in the resist, and we may have the built in stresses because of highly viscous nature of the photoresist. And so what we do after spinning is to take the wafer through a process called soft baking. Okay. So the soft baking process, it does two things. It removes the solvent, the 15% solvent that typically we use in order for the viscous photoresist to spin, is removed by the soft bake process, and also the stresses are removed using the soft bake, and the soft baking additionally promotes adhesion between the photoresist and the wafer. And because we do a baking process, the photoresist dries, the solvent gets removed, and so that is the reason we do not have to worry about sticking of the mask onto the photoresist when we do the UV exposure. Okay. So the baking process does mainly three different things. Okay. Remove the solvent, reduce the stress, improve the adhesion between the substrate and the resist, okay, and prevents sticking between the mask and the photoresist. Okay. If the baking temperature is very important. Okay. If the baking temperature is lower than what is optimal, then you have dark erosion. Okay. Dark erosion meaning some parts of the photoresist are from different points is going to remove, and it will be in the developer solution when you do the development. Okay, because the baking time is not optimum. So there will be holes inside the photoresist, okay, because it is not properly baked. Okay, that is known as dark erosion. On the other hand, if you have longer baking time than what is required, then that would reduce the development rate. If you have exposed, if you have baked the resist coated wafer for a longer time than that we need, the development time will increase, and many times the areas of the photoresist that you want to remove may not get also removed. Okay. So that is the, so to get an optimal soft baking time is very important. Now the way we bake is using hot plate. That is one approach. We can also use ovens. The hot plates have a heater at the center of the plate. Okay. And but one good thing about hot plate is that the hysteresis is low. That means the heating and cooling can be achieved pretty quickly. If you, let us say, if you increase the temperature to 95 and you want to bring it back to 70, the amount of time that you need is very less. Okay, so it has low hysteresis, whereas the heating is non-uniform. Okay, because you have a heater at the center, there is always a temperature gradient from the center of the wafer to the edge. Okay, so the heating is not uniform. On the other hand, if you go for oven, the heating will be more or less uniform throughout the surface of the photoresist, but the downside of the oven is that the hysteresis is quite long. Okay, if you set a temperature as 70 degrees, it does not go and reach 70 degrees, it goes to something higher than 70, goes to 75, comes back to 65, it fluctuates until it gets the steady temperature. Okay, so that is how we can differentiate between hot plate and oven baking. Now what we have in the photoresist, in a photoresist typically we have three different components. The major component is the polymer, which is the base holding the photoresist, and this polymer actually enables the changing of the structure when it is exposed to UV light. Okay, and then there is a component called sensitizer, which controls the photochemical reaction when UV is exposed onto a photoresist, and the third component is the solvent, which we have already discussed, that it allows spinning of the photoresist onto the wafer. Now what are the properties of a good resist? Good photoresist will stick very well to the wafer, so it would have a very good adherence and it would be sensitive to UV light. Okay, so by depending on whether it is negative and positive, accordingly it will cross link, or the links between the bonds are going to break. Okay, so it should react with the UV light. Okay, so the sensitivity to UV light needs to be good. The etching resistance to the etch solution. So what do you mean? That we use photoresist to create a pattern on the surface of a wafer or surface of an oxidized wafer or surface of a metal in some cases. So we use photoresist as a pattern. Okay, so when you use photoresist as a pattern and you want to etch the next layer underneath using a etching solution, the masking photoresist layer need to have the etching resistance, okay, to the etching solution that we are using. Okay, so it needs to exhibit good etching resistance to the etch solution, needs to have good resolution to create finer and finer structures, easy processing, we should be able to process the photoresist in a process easily. The purity needs to be high, the shelf life needs to be high, so you can use it for a longer time, low cost and high glass transition temperature. Okay, so these are the properties of a good photoresist. The coating thickness many times is going to affect the fineness of the lines or the spaces to be resolved. So we would have the precision of the photolithography, using the photoresist, the resolution may be affected by the coating thickness, because when we talk about photoresist based patterning, we are selectively removing photoresist in some portions of on the surface of the wafer, and that is because of the mass transfer between the photoresist and the developer solution. If the thickness is high, many times thickness is very high and the gap is very low, the mass transfer becomes limited. Okay, so the resolution of the structure would depend on the thickness of the photoresist. Okay. So there are two types of photoresist, one is positive, the other one is negative. In case of positive photoresist, in the exposed areas, the bonds will become weak, it will be broken, and so the exposed resist become more soluble than unexposed areas. Okay. So, if you have a positive photoresist coated onto a wafer and we expose UV light through a mask, all the exposed areas to UV light will get dissolved in the developer solution. Okay. Whereas, if it is a negative photoresist, the exposed areas will stay. In the exposed areas the polymers are going to cross link and they are going to stay. In the unexposed areas the photoresist is going to dissolve in the developer solution. Okay. So, that is going to happen in the negative photoresist. So, here are the examples of positive and negative photoresist. Positive one example is diisoquinone ester plus phenolic resin, and one of the widely used negative photoresist is SU8. Okay. So, this is what we talked about negative and positive photoresist. Let us say here we have a silicon wafer onto which we have put a photoresist layer and we are exposing UV light through the mask. So, all those blue lines are opaque. Okay. So, they can prevent the UV light. So, as we see here the exposed areas, if it were a negative photoresist, the exposed areas are going to cross link, okay, and they are going to survive in the development process. All the unexposed areas are going to dissolve. So, here in these unexposed areas where the mask is protecting the UV light are going to be removed from the wafer. So, then subsequently let us say we have another film underneath, let us say an oxidation layer which is denoted by this black line. If you can etch, so use once the photoresist is developed, we use this layer as a protective mask for etching silicon dioxide. So, this is the etching film that we get, okay, starting from here. Now, if it were a positive photoresist, in the positive photoresist the exposed areas are going to be dissolved. So, in these areas the photoresist are removed. So, we get, after we do the etching, this is the structure of the film that we get. Okay. So, once we do the coating of photoresist, the next step is to bake it. So, after we do the bake, we go for UV exposure through the mask. Okay. So, here you can see typical UV mask aligner and UV exposure system. So, here you see a typical mask aligner and UV exposure system. Here the coated and baked wafer are aligned with a mask, and this mask aligner will have the provision in terms of a micrometer and a viewing mechanism to align the mask with the wafer. And then on the mask, as I was telling, for especially for multi-layer photolithography, you would have crosshairs on the wafer which will be aligned with the crosshairs in the mask, but for a single layer the crosshair alignment is not going to be important. So, once we bring in the mask and the resist coated wafer in physical contact, then we expose the UV. Now, for the UV exposure, we have to be very careful in terms of the intensity of the light and the wavelength of the light, as well as its uniformity across the wafer. Okay. So, all these parameters are going to affect how the structure is going to look like after development. So, immediately after exposure, you can actually if you have a mask pattern and you do an UV exposure through the mask onto a resist coated wafer, after the UV exposure you can actually see the latent image getting transferred to the surface. So because the entire process is a photochemical reaction that gets initiated when you expose the UV expose the UV light onto the resist. So after immediately after the exposure you can actually see a pattern of the mask getting transferred onto the surface. So what happens in the exposure is the light the exposed light actually induces a chemical reaction. So it is a photochemical reaction. So the solubility of the exposed areas are different as compared to unexposed areas. Okay. So the depending on the property of the photoresist, if the photoresist is such that the absorbance is going to be higher, then it would degrade the resist profile. Okay. So what is going to happen is if your beam is going to come straight, then because of the absorbency, higher absorbency of the wafer, it is going to get penetrated more into the lateral direction into the photoresist. So the resist profile, if you want to achieve a flat profile, instead of a flat profile it may diverge in any direction, okay, in the lateral direction. Okay. So that is going to happen if the absorbency of the photoresist is more, whereas if the absorbency is less, then the exposure time has to be more. So you need to expose it for a longer time for the photochemical reaction to happen in case of photoresist with less small absorbency. So once we do the UV exposure, as I said, there is a photochemical reaction that is going to be initiated, and you can in fact see the pattern getting transferred. Now to complete the photochemical reaction that has been initiated, what we do is a post exposure bake. Okay. So we do a post exposure bake to complete the reaction initiated during exposure to during the UV exposure. So there are different methods that are done to achieve post exposure. One is post exposure baking. In some cases people use flood exposure, so meaning instead of going for a post exposure bake, you can do a complete exposure of UV onto the surface. Okay. So you just remove the mask and the entire surface is exposed to UV light, that is called flood exposure. In some cases people also go for treatment with reactive gases and vacuum treatment to complete the reaction that has been initiated. And typically the post exposure bake is performed at a higher temperature than the pre bake temperature, and if the post exposure is performed at the near to the glass transition temperature of the photoresist, okay, then it would reduce the stress that has happened during the soft baking and exposure. Okay. And so the post exposure will improve the adhesion of the resist onto the surface and would reduce the under etching. Okay. So what it means that immediately after spin coating you have done a baking where there is a chance that the thin film of the photoresist may show a tendency to come out of the wafer. Okay. And then again you are going for a UV exposure where it would do a photochemical reaction. Okay. That means that there is going to be a change in the internal structure of the bonds in the material. So because of which it may develop some stress inside the photoresist. Okay. So if you do a post exposure bake close to the softening point of the photoresist, it is going to reduce the stress and it is going to improve the adhesion between the photoresist and the surface. Okay. And in some cases it is also going to reduce the under etching. Okay. So under etching is etching in the lateral direction under the layer of the photoresist. So this post exposure bake at softening point is also going to reduce the under etching. Now another important thing is that immediately after doing the exposure we do not do the post exposure bake. Okay, what happens is during the exposure, because of the photochemical reaction, nitrogen is released from this photoresist. Okay. Now if you immediately go for post bake, the nitrogen would expand and try to come out quickly. Okay. So that would again promote delamination between the photoresist layer and the surface. So there is always after you do the UV exposure, you do not go for post exposure bake immediately, you do a lag. So you wait for some time and then take it to post exposure bake. Okay. And so it helps degas of outgassing of nitrogen, and it also reduces the mechanical stress. So once we have done the post exposure bake, then we want to go for development. So you dip the wafer into a developer solution. So the development process actually transforms the latent image into a relief image. So the latent image that we are able to see, if you put it in a developer solution, depending on the resist pattern and the design of the mask, it is going to remove material in some part of the photoresist. So you will be able to get a relief image that you would clearly see on the surface of the wafer. So selective dissolving of the resist would take place. As I was telling, in the positive photoresist the exposed areas are going to be dissolved, and in the negative exposed areas are not dissolved. Okay. So that is going to happen. So there are two techniques mainly to do development. There is wet development and dry development. Wet development is widely used including academia. However, wet development has got limitations that one is there may be a case where the liquid developer try to penetrate at the bottom of the photoresist. So there may be chance of under etching. Okay. There could be chance where the photoresist may be a little bit over developed, so the entire photoresist layer will fall off. Okay. So these problems are not there in case of dry etching. Okay. So in dry etching the loss of adhesion problem is not there. Okay. However, the dry etching process is quite expensive, it requires a more expensive setup. Okay. And the other downside of wet development is the developer solution that we use is not environmental friendly, whereas dry development where you just use a reactive gas or a plasma to remove material is quite environmental friendly, and the resolution is going to be much better as compared to wet development. So normally the positive photoresist are developed in aqueous solvents, something like a potassium hydroxide, and the negative photoresist are developed in organic solvents. Okay. So there is a difference between the developer solutions that are used for positive and negative photoresist, and the aqueous solvents are preferred due to health reason. They are more environmental friendly as compared to the organic solvent, but the organic solvent are cost effective, much cheaper as compared to the aqueous solutions. So that is why in academia the organic solvents are more widely used. The downside of organic solvent is going to be the resist swelling. Okay, the swelling of the photoresist when it is put in a developer solution. So there could be a problem in terms of the adhesion between the resist and the substrate. So dry development will not have such problem with in terms of adhesion. Now there is a there could be a problem while developing, it is called which is overcome by what is called descumming. Okay. So descumming is the process of removal of unwanted photoresist after development. Okay. And this happens especially for large aspect ratio structures where the thickness of the photoresist is high, or the height of the, let us say, groove is very high as compared to the lateral direction. So the mass transfer becomes limited. Okay. So it is basically the developer tries to take away, remove the photoresist from the wafer. If the width of the structure is very small, the groove is very small, then the mass transfer becomes limited. So there is always unwanted photoresist lying on the surface of the wafer, okay, which is not able to dissolve in the developer solution. And descumming is the process of removal of such unwanted photoresist. Okay. But the downside of descumming is that you would be etching the entire surface of the wafer more. So the patterned areas are also going to be thinned. You are removing the unwanted resist layer, and at the same time the already patterned layer is going to be thinned in that way. And after you do the development, if you do a high temperature baking, that is going to remove the any residual solvents that is going to present on the surface of the wafer, and it would also promote adhesion. So once we do the development of the photoresist layer, for example, as you see here, this photoresist layer act as a mask to etch the silicon dioxide layer here. Okay. So this is an Si2 layer which you are trying to etch. So the etching is performed typically on a patterned thin film. Okay. And then many times after removing the thin film, we also want to etch the silicon itself. So many times we want to go for a bulk etching of the silicon. Okay. So the etching process may involve either etching of this thin film or etching of the bulk of the silicon, okay, to form the structure of the device. So typically etching is a subtractive process, meaning we are removing the material from the either in terms of the film or the bulk of the material. We are not actually depositing material, so that is the reason it is a subtractive process. And we have two different etching techniques, dry and wet etching techniques. In dry etching is basically is based on a plasma, so highly energetic ions which interact with the surface that we want to remove. Okay. So they are mainly categorized as glow discharge method, which is plasma etching or reactive ion etching, and the second one is ion beam methods, which is ion beam milling. So energetic ions actually collide with the surface to remove the material, and we also have reactive ion beam etching. Then we would have wet etching, we are mostly based on some liquids, okay, chemical liquids that are used for etching. And so after we etch, after let us say here in this case we are trying to etch the silicon dioxide layer. So for etching silicon dioxide, this photoresist layer acting as a mask, okay. That means the etchant do not attack photoresist, but only selectively etches the silicon dioxide layer. And once we have etched the silicon dioxide layer, our job is finished, so we can remove this photoresist layer. So the resist is stripped off after the etching process. So after the etching, let us say we are trying to create a microfluidic channel, okay. We have patterned the photoresist, we have done development, then we have etched the silicon dioxide, etched the silicon also using bulk micromachining, which we will be covering later. And then so we have a open channel structure, okay. But in microfluidics we will need to seal the channel, we will need to close the channel, and this is typically done by bonding. Okay. So that bonding process would depend on what substrate material that we are dealing with. Okay. So polymers will have different bonding procedures, silicon will have different bonding procedures. If you talk about silicons, as you see here, bonding of both silicon to silicon and silicon to glass is possible, and silicon to glass is typically done by anodic bonding, and silicon to silicon is done by fusion bonding, which uses relatively higher temperature. So the material in fact goes to melting, and that is how the silicon and silicon fuse each other at the interface. And anodic bonding, we will go over the bonding process in detail sometime later. Anodic bonding uses relatively less temperature. As you can see, this is the setup where the silicon is connected to anode and glass is connected to cathode, and by applying a high voltage, the atoms at the interface are going to penetrate into each other. Okay. So the silicon atom is going to penetrate into glass and glass atom is going to penetrate into silicon. So you would achieve a bonding between the glass and silicon wafers. We can also use anodic bonding for bonding silicon and silicon, and this is possible if you use an intermediate glass layer. Okay. So after we do the bonding, the next process will be to measure the structure what we have fabricated. In some cases, let us say you have made a channel, before bonding you can check what is the depth, what is the width that you are measuring, and you can compare that with your original design. Okay. And this is typically done using a profilometer. Okay. Profilometer is one approach that you can use to measure the dimension of the fabricated structure. Okay. For example, a microchannel. We can also use scanning electron microscopy SEM to image and determine the different sizes. Okay. So we go for profilometry to characterize the dimensions of the device. Alternatively, we can also use things like SEM. Okay. Once we have done the bonding, the next step would be wafer dicing. Okay. Because when you do a fabrication on a single silicon wafer, we may have many devices printed. Okay. So in order to separate the devices from each other, we would have to dice the silicon wafer, and this is done using a special silicon dicing machine. Okay. And so first we scribe the wafer and then break it. Silicon is a very complicated material, depending on the crystal plane and the crystal structure and orientation, we would have to scribe it accordingly and break it to dice. Okay. Alternatively, it is also done by laser cutting. Okay. So both mechanical sewing and laser cutting are used for dicing of wafers. The next step typically would be to do what is called wire bonding. Okay. So in micro devices, including microfluidic devices, we would have many times fluid integrated with electrical electrodes. Okay. So in order to establish electrical connection between different parts of the electrical network on the chip, or the electrical connection between the electrodes on the chip and the external electrodes, we would need to make electrical connection. Okay. Since the dimensions that we are talking about are very small, we may not be able to always use solder, for example. Okay. So at such small dimensions with small precision requirements, we use what is called the wire bonding. Okay. So this is used for making interconnections between chip and the rest of the device during device fabrication. There are different materials that are used: aluminum, copper, gold. They are most widely used in the wire bonder. So that gives a broad overview of the photolithography process. Now let us talk about the deposition techniques, the first step where we talk about two things. One is the doping, okay, which is used to increase the conductivity of the silicon wafer, especially for electrical applications. We need to control the conductivity of the semiconductor itself, okay. So since we are talking about silicon based microfabrication, let us try to understand what the doping method is, and then we will also discuss oxidation, okay, as part of the additive techniques. So the deposition techniques are have importance in micro devices, especially when we are talking about chemical and biochemical sensors, in microfluidic devices as well, because we are talking about putting conducting materials on the surface of the wafer, either using deposition technique, for example using evaporation or sputtering. So this is required to make enable electrical connection between the chip and the external wall, okay. So to deposit materials or metals on the substrate, it can be deposited from different sources, from liquids, plasma, gas, or in some cases from solids, okay. And these deposition techniques are actually done at high temperature. So they need a thermal processing to undergo to achieve the deposition. Here are some of the materials that are used for deposition on micro devices, and we will be talking about different additive techniques. We will be talking about doping of the silicon and oxidation process, the detail of it. So after we cover these two, we will also talk about the deposition of different selected metals that are presented here. So we will be talking about two important techniques here. We will be talking about physical vapor deposition, namely the evaporation and sputtering, and we will also talk about chemical vapor deposition, okay. So let us first talk about doping of silicon. So as I was saying, what does doping do? Doping basically modifies the impurity level in a semiconductor like silicon substrate, okay. So the conductivity gets modified, okay. So the doping, as you see here, it adds impurities into crystal, so the thermal the electrical conductivity gets modified. So what we do typically is we add elements that have one valence electron more or less than that of silicon. So silicon has 4 valence electron, and we add metals that have either one more or one less as compared to silicon, okay. So the one that has got one less is known as N type, and the one that has got one more is called as P type, okay. So these are some of the dopants that are used: boron, phosphorus, arsenic, antimony. So the dopant would receive or give electron from the crystal. So some of the important sources that are used for doping, this is PH3, which is phosphine, and BN3, boron, okay. So these two are important two sources. One is the phosphine is a gas and boron is a solid that are used for doping the silicon, okay. And we have mainly two important methods that are used for doping. One is diffusion, and the second one is ion implantation. So if you look at doping, we are basically trying to improve the electrical conductivity and which is given by this expression here. Sigma is the conductivity, which is E here is proportional to E. E is the charge of an electron, and N is the number of negative charge carriers. Mu E is the mobility of electron, mu P is the mobility of protons, and the P is the number of positive charge carriers. Okay. So the conductivity can be defined in terms of these parameters. The resistivity is defined as 1 over conductivity, as you see here, and the resistance is R equal to resistivity into length over area of cross section. Okay. So if you see this typical conductor here, which has thickness T with W and length L, and current I is flowing perpendicular to the cross section W into T. So you can write the resistance R is going to be resistivity into L over area is W into T. So here we can define the resistivity over thickness as something called seat resistance, okay, into L over W. So this seat resistance, the unit is ohms per square. Okay. So this is seat resistance, which has unit ohms per square, and L over W is the number of squares we have. So the L of the substrate could be very high. So then W, if you divide L into equal number of W's, okay, then you can find how many number of squares we have. Okay. L by W stands for number of squares, and RS is the seat resistance, which can be measured using different techniques, including the 4-point probe technique. So this is the basic of the conductivity and the resistance of the typical conductor. So next we talk about the doping by diffusion. Okay. So the diffusion of dopants occurs between the silicon substrate and the gas present in the furnace, which is typically at a temperature 950 to 1280 degrees centigrade, and this diffusion is governed by the Fick's first and second law. And if you look at Fick's first law, which says that the dopant flux is proportional to the concentration gradient. Okay. So F is negative of D is the diffusion coefficient into del C over del X is the concentration gradient. Here X is into the substrate. Okay. So this is X, this is, let us say this is the surface, X is into the substrate. Okay. And the Fick's second law tells that the flux gradient del F over del X is proportional to the change of concentration with time. So this is the concentration change with time, the gradient del F over del X is proportional to the change of concentration over time. So there is a negative sign here because the flux would reduce with increase in the X. So again, if you use the expression for F from the Fick's first law, this is the equation you get. Okay. Now to solve this equation we need boundary conditions. Okay. So we need two boundary conditions here. So these are two boundary conditions. The concentration of at the surface Cs is constant. We assume that there is infinite supply of the source, so that the surface concentration is going to remain constant, and the concentration is going to reduce to 0 in the bulk. Okay. So C 0 T is Cs and C infinity T is going to be 0. So using these two boundary conditions we can find the expression for how the concentration is going to vary with X, that means how the concentration is going to change with the depth into the substrate. So it follows an error function trend. This is the complementary error function, and Cs is the surface concentration, and we have square root of dt. The square root of dt is the diffusion length, okay, and lambda equal to square root of 4 dt. If we define lambda as square root of 4 dt, that will be known as the characteristic diffusion length. That means it is the measure of distance where the diffusion of the concentration is going to reduce to 0, okay. So it will be Cs at the surface, very high at the surface, and it is going to reduce to 0 at a distance which is square root of 4 dt, okay. So this is assuming that the surface concentration remains constant. So next we will look at if the concentration is limited, then how the concentration profile is going to look like. So we will continue on that. With that, let us stop here.